Hello, my name's Matthew McIlree. I'm a PhD student at the University of Glasgow, and this is going to be a talk on what's been the main focus of my PhD research, which is getting a constraint programming solver to output a proof. And I'm specifically going to talk about how we use pseudo-Boolean proof system in order to do this in the very PB proof system, which of course has been the focus of this WHOOPS seminar workshop. So first of all, I'm not going to assume too much knowledge in this talk. So although there will be a little bit of overlap between some of the other talks in the session, I'll try and just quickly explain everything from first principles. So to start off with, what is constraint programming? At one level, this is just a method for specifying problems. So we have a set of variables, a set of possible domains for those variables. Those are the values that the variables can take, and constraints that restrict the allowed combinations. So if we want to take a very abstract view, the variables are just symbols, the domains are just sets, and the constraints are just predicates that restrict the allowed values. And this very high level abstract view allows us to be very smug in constraint programming and see all other combinatorial solving paradigms as being special cases. So in Boolean satisfiability, we can say this is a constraint programming problem where the domains just all happen to be Boolean 0, 1, and the constraints all happen to be propositional clauses. We can also say, for example, mixed integer programming is constraint programming where the domains are just real numbers or integers, and the constraints are all linear equalities or inequalities. But in practice, when people actually talk about constraint programming and the discipline of constraint programming, we're talking about something a little bit more specific. So we're talking about when the domains are all finite ranges of integers, usually, and the constraints come from some predefined set or constraint programming toolkit. So this still allows us to be very high level and very abstract, but kind of restricts the problem domain to something that can be efficiently solved in many cases by constraint programming solvers. So in our constraint toolkits, we normally have arithmetic constraints like z times w equals 5, not equals constraints, and the usual linear combinations and these kinds of constraints. But we also have more expressive global constraints that operate over non-fixed sequences of values. So a good example of this would be the AllDifferent constraint, which says quite obviously that all of the values of these variables must be different. And we have all kinds of crazy things on top of that. For example, regular language membership that says this sequence of variables must be recognized by a deterministic finite automaton, which you specify as part of the constraint. So this can be an extremely expressive way of writing down problems and is obviously used for solving real world problems in many cases, and for puzzles and for various other things. Now, to turn the constraint satisfaction problem into asking, can we satisfy these constraints, into asking what is the optimal value for some variable or set of variables, we can also specify an objective function. So that would be a constraint optimization problem on top of a constraint satisfaction problem. Now, constraint programming as a term also refers to the solving methodology. So there are specialized constraint programming solvers for solving problems specified at this level. So obviously we have the option of encoding down to a lower level format, but often we can take advantage of this high level structure and get some interesting solving techniques. So the main techniques in constraint programming, I'm going to categorize under inference and search. So inference, what we usually mean is looking at a particular constraint and some values in the domain of variables in scope of that constraint, and then just removing values from the domains of variables based on what the constraint is telling you. And we talk about enforcing different levels of consistency on the variables in scope. So if I ever mention domain consistency, this is like enforcing what is the highest level of filtering that you can, taking values away from the domains of variables. So you can think of it as going through the domain and poking all the possible holes. So for example, if x equals y plus 2 and y has this domain, then if x had all of these values initially in their domain, we can poke all of the holes where x is 2 less than a value of y. So that would be all of these values. So this would be enforcing domain consistency based on this admittedly not very exciting constraint. We also sometimes talk about bounds consistency, which is a weaker level of enforcement and is sometimes more efficient to actually implement in practice, where instead of poking all of the possible holes, you just narrow the min and the max value. So in this case, if x has all of these values in its domain, we would remove the minimum value, so bring 3 up to 4, and reduce the maximum value, so bring 11 down to 9. So that's domain consistency, bounds consistency. These are inference techniques. And inference can be different depending on all the different constraints that you're using. So for different constraint types, we probably have specialized inference algorithms. And we sometimes call these constraint propagators or constraint filtering algorithms. So if I use any of these terms, they all mean the same thing. This is kind of a fundamental aspect of constraint programming, is implementing these different algorithms. But obviously inference can only get you so far sometimes. So we also do backtracking search and other kinds of combinatorial search. So you're probably familiar with the idea of backtracking. This is just making guesses until you reach a solution that is just simply infeasible. And at that point, you undo the last guess and guess something else. Now, I'm going to assume here that you're guessing values for the domains of variables. So I'll guess x0 is equal to 1, for example. But you can also partition the search space in various different ways. And this all comes under backtracking search. And the idea in constraint programming is usually that you're running a search algorithm and performing inference along the way in order to get to a solution nice and quickly. Now, there are other search methods as well in constraint programming. We do have a version of conflict-driven search borrowed from Boolean satisfiability, or at least primarily developed in Boolean satisfiability, and there are also local search techniques. For the purposes of this talk, I'm going to talk mainly about backtracking search. So that's the kind of the main one that we'll focus on. And what do we actually want in this talk? What am I here to say? Of course, we're talking about proof logging. So even though if you've seen the other talks in this series, this won't come as a huge surprise to you. We'll just recap the basic idea. So normally you give this constraint programming description to a constraint programming solver, and it gives you an answer. But the solver is acted effectively as a black box. So what we would like is for the solver to also produce a mathematical proof of correctness that certifies that that is indeed the answer with respect to this problem description. And then the hope and the idea is that this proof, the answer, and the original description can be fed to an independent proof checking program that will tell you whether or not the proof is valid for that answer, and thus whether the answer is indeed the answer for this problem description. And the idea is that the proof system, of course, should be set up so that mathematically it's impossible to have a correct proof of an incorrect result. So if your solver ever gave the wrong answer, you'd be very able to detect this. And on top of that, as Jakob talked about in the introductory talk for this session, this gives you many other benefits as well for debugging your solver and also for auditability, getting a record of what the solver actually did. So CP solvers being exact algorithms, it seems very possible that we should be able to do this. And indeed, in the past, constraint programming experts have been quite keen to try and get CP solvers to do something like this. So there has been a few attempts before to do proof logging for constraint programming. And one of the interesting things is, obviously, we have all of these different inference algorithms, and some of them are doing very deep, almost reasoning and using quite high-level techniques. So an assumption is that a proof system for a constraint programming solver that could be checked externally would somehow have to have all of this inference information built into it. So it would have to be able to understand the techniques that the solvers are doing and check them on that level, which effectively means we would have a trusted inference checker of some kind for every constraint, or as another way of thinking about it, a rule in the proof system for all of the different constraint types. And although this has been prototyped and was an early approach, there are some drawbacks with this idea. First being that you're putting the onus on the proof checking software to understand all the things that your solver is doing, which means that if you ever want to do more in your constraint programming solver, you always need to modify the checker in order to keep up. And the second thing is that there are just a lot of constraint types and a lot of different propagation algorithms. And so this really takes the checker from being a simple piece of software that we would absolutely trust in and of itself to being potentially almost as complex as the solver itself, which kind of philosophically comes up against the main idea of proof logging, where we want the checker to be a really simple piece of software. So we want to be able to capture all of these reasoning techniques in a proof system that is both simple enough to be easy to verify, but also expressive enough to capture all of the different kinds of CP reasoning in a way where you can write down everything that a CP propagator or inference algorithm does as a sequence of proof steps in that proof system without having to modify it every time or introduce a huge number of proof rules. And obviously, this is the Pseudo-Boolean proof system session, and we're at whoops 2025. So, of course, as we've heard in other talks, Pseudo-Boolean proofs would seem to fall into this sweet spot. So, the very PB proof system is what I'm going to talk about and use in this talk. As we've seen already, Pseudo-Boolean constraints can be very expressive and much more than you just think, being 0, 1 integer linear inequalities. And the associated proof system that very PB is built on, the fundamental idea is cutting planes, and this can be quite powerful and implement powerful reasoning. This already has a working proof checker and formally verified implementation, which we'll hear about, and has been used for certifying solvers in a wide range of combinatorial solving paradigms, including our work on CP and the graph algorithms my supervisor Kieran talked about in the previous talk, and also SAT, MaxSat, and of course for PB solving itself. So although it is very PB and it's Pseudo-Boolean constraints, it is of course not directly intended to be just for Pseudo-Boolean solvers. It is a general purpose proof system, and when we use it for constraint programming, we intend to use it as such. So although other talks have gone over this material, I'm going to just give a brief recap on the basic ideas in Pseudo-Boolean solving and in Pseudo-Boolean proofs. So when I say PB variable, I just mean a Boolean variable, but really it's a variable with the values 0, 1. We just interpret 1 to be true and 0 to be false. Then a literal, which I'll often just use the curly L to notate, is a variable or its logical negation, which is just a substitute for 1 minus x if we just put a bar above the x to mean not x. Then a PB constraint is a linear combination of literals, and it needs to be an integer linear combination. So this is a 0, 1 integer greater than constraint, if you like, and that's what we'll call a PB constraint. And we'll always assume, as the proof system requires, that the constraints are always in the greater than form. Then a Pseudo-Boolean model or formula. Model can be a bit of a confusing term, so I'll try and stick to formula where possible. It's just a set of PB constraints that obviously on its own specifies a constraint satisfaction problem, albeit of a very restricted form. And it can also have an objective function specified as well, which has to be itself a Pseudo-Boolean linear combination. So this is the way of specifying Pseudo-Boolean problems. Then a Pseudo-Boolean proof is just taking a Pseudo-Boolean formula or model of a problem and then deriving from it Pseudo-Boolean constraints that preserve the satisfiability of the original formula. So basically, whenever we derive a PB constraint by a particular rule in the very PB proof system, that constraint is guaranteed not to affect either the satisfiability of the formula or the eventual optimal solution. So this means that if we derive in sequence a bunch of Pseudo-Boolean constraints and then eventually derive a constraint like 0 is greater than or equal to 1, we have found that the problem is unsatisfiable because it was equisatisfiable with this obviously false constraint. If we're doing an optimization problem, as we might well be doing in constraint programming, we want to derive bounds on the objective function. So we need some way of specifying this is a solution to the problem and then deriving either contradiction from a bound that says we must do better than this, or just deriving upper and lower bounds on the objective function directly. Now, I've written this all in mathematical notation, but it's worth remembering that everything here can be expressed in an ASCII text format. So we have OPB files for the problem description and PBP files for the Pseudo-Boolean proof system. So that's the recap on Pseudo-Boolean proofs. Now, obviously, you'll realize pretty quickly that I've just talked about these general constraint satisfaction problems where we have high-level constraints and finite domain variables. But yet this proof system that I want to use only knows about 0, 1 variables and linear constraints. So we do have a caveat to being able to use this general purpose Pseudo-Boolean proof system, and that is we can't just give the problem description to the independent proof checker directly. We do have to encode it to PB form first. So this slightly modifies the basic proof logging idea. Now, the PB encoding is not used for the solver, so this doesn't mean we're turning our CP solver into a PB solver. It just means that we're specifying the problem now in a language that the proof checker can understand. Now, at the moment, this is an unverified component of our system, which potentially makes it a little bit of an Achilles heel from the certifying correctness point of view. But we do use kind of the same logic as we use as saying that we should trust the checker, in that the PB encoding should be a much simpler piece of software that we trust in and of itself, or we can work on looking towards formally verifying the actual encoding with respect to the original high-level problem description. And I'm going to argue this is a reasonable thing to do, in part because of the expressiveness of PB constraints. So we can specify problems at this high-level CP level and turn them into PB problems actually with quite a lot more ease than you might think, particularly because we don't need to worry about making these problems easy to solve from a solver's perspective or using smart encodings that propagate well. We just want obvious correspondence with the original problem when we write an original CP problem into a PB problem. So I'll go through a couple of ways in which we do this because it's quite fundamental to everything else that we do. So starting off, we obviously need a way of encoding our CP variables and talking about them in PB terms. So we're going to use, like all things in computer science, a good bit of binary. So if we have, like we're assuming all variables as finite ranges, then we can always represent those variable values with a finite sequence of bits. So if x was between 3 and 10, we could represent this with just 4 bits. And then we can evaluate this bit representation. So use a PB variable for each bit value and evaluate it just as a linear sum using the place values of the bits as the coefficients. And this is great because it allows us to just constrain that these bits have to be between 3 and 10. So here's a greater than equal 3 constraint and a less than or equal 10 constraint, and just treat that sequence of bit variables, these PB bit variables, as the CP variable. So in our PB model, this is what X is. It is this sequence of bits. And this is quite a straightforward, easy thing to do. There's no problem with negative values either. We just use a 2's complement representation. So treat the most significant bit as being negative. And this also just allows us to write the value of X as being a bit sum and constraining it between negative 12 and 10. Now I might be lazy and not actually write out all these bits every time. So if you see me writing just bits brackets X, just remember this is a substitute for that exponential sum over bit variables. And what's very cool about this is it means we can effectively just squint at our PB model and pretend that we have finite domain variables, even though we only have these 0, 1 variables. So this allows us to encode linear constraints completely directly. Like, for example, x plus 2y minus 4z is greater than or equal to 11. We just substitute in all the bits, and that gives us a representation of that constraint just directly. And I don't think anyone would be in any position to doubt very much unless you doubt the fundamentals of binary representation that these are the same constraints and these have the same effect on these bit variables as this did on this original finite domain variables. So that's the first thing. Okay, the second thing that makes PB constraints quite expressive is that we can natively what we call reify them. So we can make them conditional on other 0, 1 variables. So if I have just like an arbitrary PB constraint like this, I want to make this conditional on some other PB literal, we'll call it y. So if y is true, then this constraint should be enforced. And if y is false, then we don't care. And these semantics can actually be implemented completely directly. If you're used to integer linear programming, you might know this as big M notation. So in PB terms, what we do is we put a large enough coefficient in front of the negation of that variable. So remember, this is just 1 minus y, or literal. This works for literals too. And if we think about this for a second, this means that if y is ever false, then this becomes 1. And this coefficient is so large that the constraint is now just trivial. So negative 14, it doesn't matter how we set any of these values. There's no constraint on these variables anymore. But then if y is true, then this becomes 0, and then we do actually have to satisfy the constraint. So this has the exact semantics of an implication or a reification of this PB constraint. And this is nice as well because we know how to express, obviously, the negation of greater than equalities. It's just writing down the less than, which is just negating the coefficients and adding 1 to the right-hand side. So we can always write stuff like this as well. Why if and only if this PB constraint. And this would be why implies the constraint and not why implies the negation of the constraint. So if I write this, that's what this is a shorthand for. We can also just nest this as well. So if we have a collection of PB literals, we can say the conjunction of them all implies a constraint as well. And this is just effectively nesting a bunch of reifications. So they all just get the same large coefficient in front of their negation. So these are all things that we can do natively inside the PB proof system and express these kind of logical connectives, which makes it very easy to sort of build up a representation because effectively I can assign Y the meaning of this entire PB constraint and then go on to use Y in other PB constraints and thus build up quite a complicated representation from there. So this sort of thing makes it very easy, in fact, to encode CP constraints. So I'll show you a few just random examples. So take x not equal to y and x not in this set 3, 5, 7. These are very standard sort of CP constraints. So to say two variables are not equal, all we need to do in PB terms is take the bit representations of the variables and reify the idea that they are either greater or less than one another with a flag. And the flag is either going to be true or false because it's just a 0, 1 variable. So we say flag implies bits of x is strictly greater than bits of y, and not flag implies that the bits of y are strictly greater than the bits of x. And obviously, these are going to have to be like one or the other because it's a flag and it has to take either the value 0 or 1. So this is exactly the same thing as saying that x is not equal to y. And again, I'm going to argue, you can look at that and say, yeah, that is exactly the same constraint. There's really not too much question about that. Now, if I want to talk more specifically about actual values in the domains of variables, this would be a little more fiddly and awkward to do with bits because we'd have to somehow use the bit representation to encode this not set notation. But this is actually straightforward to do as well. If we just use the trick of reifying to define PB variables that talk about values in particular domains. So what I'll do is I'll define a PB constraint, first of all, that says x is greater than 3, and double reify that on a fresh variable. And this variable is just now going to have the meaning x is greater than or equal to 3. And I can also do this for x less than or equal to 3. And now I can define a PB variable x equal to 3 if and only if x is both greater than or equal to or less than or equal to 3. And so this took 6 PB constraints in total to define. And now we're talking about just one particular equality variable. But once we have these, we can then reuse them over and over again in different constraint encodings. And this allows us, if we define the rest of the x equal variables like this, to talk about x not being in a set with just one PB constraint, because we just need to say x is not 3 plus x is not 5 plus x is not 7 is greater than or equal to 3. So that's just saying all of these literals must be true, and thus x can be none of these values, which is the same as it's not appearing in this set. So we can talk about individual variables, we can use the bit representation, and we can use flags and additional reifications as we need. So hopefully this idea is slightly more convincing now that it's not too difficult to encode CP problems to PB problems, and it shouldn't be in principle too difficult to formally verify this process, because as a human, we can look at this and say, yeah, this seems to make sense. This is indeed the same problem that we're looking at. So if we are happy with all that, then we can start with our PB encoding of the model and see if we can get the CP solver to output pseudo-Boolean proof steps among the solving process in order to certify its result. So let's talk about how we actually do that. So fundamental to what we do in CP proof logging is going to be just one rule. So I'll spend a little bit of time just re-explaining that, just in case it was lost in earlier talks. So this is the RUP rule. So this is reverse unit propagation. And the basic idea is we start with our PB model, our PB formula, I should say, and we've already derived a bunch of things. And now we want to derive a constraint from the PB model and previously derived constraints. And we're going to say it follows by reverse unit propagation. So what the checking process for this is, and what the requirements that you have to meet are, is if you take all of the constraints in the model and all of the constraints you have previously derived and add on the negation of this constraint that you now want to derive, then the checker runs unit propagation and then arrives at a contradiction. And that's when you're allowed to introduce this constraint. So we're saying basically this constraint is obvious enough that the checker can just discover contradiction from the negation and find this is safe to add. So unit propagation, it doesn't really matter so much what this is. You can think of it as just simple dumb reasoning that the checker can perform, in particular looking at each constraint and setting any variables that simply must be set in order to satisfy the constraints. Now, why this works on a kind of proof system soundness point of view, this is the way I like to think about it. I don't know if this is necessarily the best way of thinking about it, but I think if you can introduce a constraint C from a formula F by RUP, then what the checker has shown is that adding the negation of C to the formula gives you contradiction by some simple reasoning procedure, which is the same as saying that F and not C is always false, i.e. not F or C is always true. That's just the logical negation, which of course, if we know how implication is represented, means that F implies C. So everything that satisfies F satisfies C. And so of course, C does not affect the satisfiability of the original formula. So this is RUP standing for reverse unit propagation, which is a bit of a holdover from SAT. Obviously, the unit propagation that we actually use in pseudo-Boolean constraints is a generalization of this Boolean satisfiability unit propagation idea. So to give you a little idea of something that is RUP in the pseudo-Boolean proof system, and this is quite useful for CP because it is related to the properties of this binary encoding that I showed you before, and also gives a useful refresher on just what RUP is. So I'll show you this here. So if we have in our model or previously derived a constraint like bits of x is greater than or equal to 6, so this is just a binary 3-bit representation of a CP variable x, then we can derive some obvious facts like, for example, bits of x are greater than or equal to 3. And this is because when you take the negation of this constraint and add it to the model, which in this case is just one constraint, we effectively get contradictory bounds on these bit variables. And this, in fact, will always unit propagate to contradiction by a sort of argument that we've found we like to call just ping-ponging. But if you just look at this and work through it, you can see how this happens. So looking at this bit representation, in particular looking at the most significant bit, 4x bit 2 here, clearly bit 2 has to be 1. Because if bit 2 was 0, then the remaining 2 bits can only make up to 3, and so of course we're not going to get over 6. So the unit propagation procedure sets this to 1 as part of the checking process. Okay, but now we have to set x bit 2 to 1 in the other constraint as well, which means we have minus 4 going over to the right-hand side, which makes 2. And this would be fine, except we've now got a bunch of negative values on the left-hand side of this second constraint and a positive value on the right-hand side, which means this constraint is on its own a contradiction. So this is what we mean by arriving at a contradiction after unit propagation. And so the checker goes, okay, I found a contradiction here after performing unit propagation, and hence this original thing, so not the negation from the checking process, that is safe to introduce. And so this is very handy. And this argument effectively bases a bunch of things that I'll talk about when I say this will definitely follow by RUP. They're a little bit awkward to actually sit down and prove in general why these unit propagation properties always happen, but we've set things up quite carefully in the proof system so that we can rely on this. And I have sat down and proved it all now for my thesis. So I can assure you we can rely on unit propagation properties such as this. Okay, so I've set up this RUP proof rule. Let's talk about how we can actually use this to do proof logging for example, backtracking search, which is one of the main constraint solving techniques and kind of fundamental to how most or a lot of constraint programming solvers work. Certainly, if we can't do proof logging for this, we don't have too much hope of being able to do proof logging for any other techniques. So like I said, backtracking search is where you're making guesses for the values in variables domain, and then when you reach a contradiction, you have to undo the last guess and then backtrack. So the proof logging procedure for this is very similar to what Jakob described for proof logging for DPLL in SAT solving, which is whenever you reach a contradiction, you have to output a constraint that encodes the negation of the sequence of guesses that led you to contradiction. And this should hopefully be a RUP constraint, or at least that's what we're going to aim for as the invariant of our proof logging method. Now, to write down the sequence of guesses, I already talked about how we talk about a variable equaling a certain value in the PB system. So we're actually just going to use PB variables to talk about x0 being not equal to 1, or x1 being not equal to 1, or x2 being not equal to 1. So this is the actual constraint that the CP solver would write out. So somewhere in the solver's code, there would just be a print statement that would output this RUP step. And we do this every time we backtrack. So if we guess something else, say x2 is equal to 2, then we would output this RUP step. And now imagine x2 only had 1 and 2 in its domain, so we're now going to backtrack from x2. So now we would output this as a RUP step. x0 is not 1, or x1 is not 1. So if we continue to do this for the full scope of our backtracking search algorithm, effectively what we're going to get is the solver's full backtracking search tree written down in the proof system as a sequence of RUP steps over these equality variables. And remember, this is not exactly what the proof would look like, because I'm writing this in mathematical notation. So again, we have ASCII text representation of all of these constraints. So this is what the solver would actually print out. Except this isn't quite enough on its own, unfortunately. So I said before we need to define these variables, and they wouldn't necessarily have been defined in the model. And also, this RUP procedure, I described it before as simple dumb reasoning and just setting 0, 1 variables based on the PB constraints. And there's really no reason at all to expect that this would reflect the potentially high-level reasoning that the solver's doing. So I showed you before all of these inference algorithms and different constraints we might be using. So if we guessed x0 is 1, x1 is 1, and x2 is 1, we might have run some very complicated procedure to determine that the constraints are now conflicting. It's not just as simple as plugging in the values. So although this works as the skeleton for our proof system, we actually have to log more things in the proof in order to get all of these things to follow by RUP. So it's all of these things that go in between that actually where the interesting work comes in. But this is the framework, and this is what we're aiming for, and the overall skeleton of our proof system. So a couple of questions. First of all, how do we define all of these variables? So I showed you before, we can define equality variables like x equals 3 in terms of greater than and less than variables, and in turn in terms of the bit representation that should be present in the model. But we don't necessarily know in advance what solving path the solver is going to take, and we certainly don't want to have to define all of these equality variables for all of the values in a variable's domain. CP solvers sometimes work with variables with hundreds or even thousands of values in variables domain and talk about them very efficiently in terms of interval sets, and just writing down every single one-hot encoding equality combination is going to be very inefficient to do that ahead of time. But what's quite nice about our proof system is these reified constraints can be derived directly in the proof system as and when they are needed using the RED rule. So the RED stands for redundant space strengthening, which Jakob talked about a little bit in the original talk. And this is a very powerful rule that allows you to do all kinds of exciting things in the very PB proof system. But for us, and the main reason it's useful for CP proof logging, is it's the rule that lets us introduce reified constraints on fresh variables. So because we're assuming this x equals 3 variable hasn't turned up anywhere else yet, the first time we decide we need an x equal 3 variable, we introduce these 3 constraints, or these 6 constraints technically, by redundant space strengthening. And then we always have a definition of x equals 3 that we can use. Okay, so that's how we relate these equality variables to the bit variables. But in terms of actually getting the solver to propagate, or sorry, to get the checker to propagate the same reasoning that the solver does, the second thing is we need to log justifications every time we infer something. So what do I mean by justification? So specifically in the context of CP proof logging, a justification, I'm going to say, is just a PB constraint of this particular form. Reason implies inference, where the reason is enough PB literals to describe the state of the solver at the point it made this inference, and the inference is the domain change that the solver actually made at that point in search. So the idea is every time the solver removes a value or a set of values from variables domains, we have to somehow derive in our proof system this form of constraint. And the idea for getting this all to work is that the reason should be something that propagates under the negation of the sequence of guesses in our backtracking RUP procedure. And then the inference will be available to the verifier and our whole RUP procedure will work out. So just to make this concrete, if, for example, the solver guessed x is 0 is equal to 1, and then x1 was found to be not equal to 2, we would derive in the proof system something like x0 equals 1 implies not x1 equal 2. Now, this might be RUP, it might not be RUP, we might have to do more work. This is the whole sort of research area of writing down all of the CP solver's reasoning in terms of these PB constraints. And the sort of weird thing that we've been discovering the whole way through is that actually cutting planes seems to allow us to derive these things from the PB definition of the CP constraints efficiently. And somehow we're not really even sure why. Still to this day, this keeps working out so well, but we've been able to go through a large number of CP constraints and find that this continually works. So that'll be what the rest of this talk is actually showing you how this works in practice. So up to this point, I've just been telling you effectively the rules of the game. So what framework we're working in for CP proof logging. So just to summarize, we use red/reification to introduce these 0, 1 variables that talk about values in the domains of CP literals that we use in the domains of CP variables, and we use the binary representation to represent CP variables. We write a RUP step at every backtrack. I didn't actually mention this, but we can also turn this into an optimization proof, providing we log solutions and derive bounds as well. This isn't too important because this effectively boils down to an unsatisfiability proof as well. So we're really just focused going forward on proofs of unsatisfiability. And then we interleave these derived justifications to account for constraint propagation. And this is where the actual interesting research is and why we think pseudo-Boolean proof logging is very promising for constraint programming. So to get to the good stuff, well, there is still some time. First good news is that some constraints are really amazingly easy. They only require a single RUP step to actually derive these justifications. So take before the not equals constraint, which is absolutely fundamental to everything that CP solvers do. The inference for this is very basic, but it's obviously very needed. So if, for example, we have x in some domain, 1 to 15, and we've narrowed the domain of y down to being just 5, so we know for a fact y is 5, the CP solver will derive or infer that x is not equal to 5. So we want to justify this in the proof as soon as it happens. So this is precisely what we want to justify. Y is equal to 5 implies that x is not equal to 5. That is obviously a sufficient reason for this. So what we first do is we need to make sure that these equality variables are derived. Now, if we'd used them already somewhere, we might already have them to hand. But if we've not used them, like I said, we'll need to do redundant space strengthening to actually introduce these equality variables defined on the original bit representation. So this is y equals 5, and this is x equals 5. So we have these PB constraints somewhere, and we have the definition of not equals that I showed you earlier. And now this is just RUP. And actually, we can see this on the bit representation because we get the contradictory bounds once we propagate through all of these equality definitions. So I won't show you the full RUP argument, but hopefully you can trust me. This will just always be RUP, which is great because we write a not equals propagator into our CP solver. And all we need is, aside for some bookkeeping to make sure we have all the red literals in place, we just output one RUP step every time we do this. So this is extremely straightforward. Other constraints will require more than just RUP, and this is why we have a more powerful proof system than just RUP. So we saw before a linear inequality constraint like this one, and we know we encode this just by substituting all of the variables for bit strings. Now, the kind of inference a CP solver might make here is if we knew that x is greater than 5, z is greater than or equal to 3, then we can infer that y is less than or equal to 6. And this is relatively easy to see. We just multiply out by the coefficients. So this first coefficient, 2x, must be greater than or equal to 10. And this third coefficient, z, must be greater than or equal to 12, if indeed x is greater than 5 and z is greater than or equal to 3. So that means that y can't possibly be 7 or any bigger than that because this would then be 21, and taking the sum of these things would take you to more than 42. So we can infer, the solver can infer that y is less than or equal to 6. So this tells us exactly what we want to derive in our proof system to justify this propagation. And again, we'll make sure we have defined the greater than variables, so x greater than or equal to 5, and z greater than or equal to 3, and y being greater than or equal, less than or equal to 6. And I'm using the negation of this here because this is the thing we actually want to infer. And remember, we have in the encoding, I'm saying this is an axiom because it comes from the problem description, this linear sum on the bit variables. So what's really nice about this is we can now just do cutting planes. So cutting planes allows us to derive linear combinations of constraints, as we've seen. So we specifically multiply each of the CP literal definitions by their corresponding coefficient in the linear and just add them all up. And we can actually see exactly why this is all going to cancel out with the definition of the less equal constraint. And this is just a sum, and this gives us exactly what we want. This is the derivation. So this means when we're actually doing this in a CP solver, again, although it's something we need to calculate or we need to figure out exactly which things to add up, which is just a tiny bit of bookkeeping, a very quick algorithm to run during the propagator's inference step, but it does actually just amount to, again, one print statement because we just need to write down these coefficients. We saw in other talks reverse Polish notation for a quick way to write down this in the very PB proof system and just justify this using a single sum constraint or a single linear inequality. Okay, so we do also have some more exciting constraints that require, again, just a little bit more thought on how they can be justified within this proof system. And this, we saw this example already in Kieran's talk, but I'll talk about it in a constraint programming sense rather than a subgraph solving sense. So it is the same example. So we have v, w, x, y, z. These are all CP variables, and we're imagining we've narrowed the domains of variables to be down to just these values. So v in 1, 4, 5, w in 1, 2, 3, x in 2, 3, etc. And if you look at this, you will notice that we have four variables with only 3 values between them. So if these have to be all different, then we've got four, whatever way around you want, 4 holes and only 3 pigeons to put in them, or 3 pigeons and only 4 holes to put in them, whatever way around you want to say it. But this means that these, of course, cannot be participating in a satisfying all different constraints. And so if the CP solver has got to this point, even though we've not actually narrowed the domain of any variable down to a single value, we should already be backtracking here. So what I'm going to do is I'm going to write down a reason. So remember, we're trying to derive reason implies contradiction here because the solver has inferred contradiction. And the reason is just going to write down all of this domain information that allowed us to derive contradiction. So in particular, it's just these 4 variables. So we have w between 1 and 3, we have x between 2 and 3, we have y between 1 and 3 and not equal to 2, and z between 1 and 3 and not equal to 2. So this reason, we have to have all these literals defined, obviously, but encodes the entire domain state at that point. And now we've got a more interesting justification algorithm for AllDifferent. So what we're going to do is we're going to derive, first of all, at least one constraints over the current values in the domains of variables based on this reason. So we can do this, and it's pretty easy to see why this will be RUP, because the reason propagates w greater than 1 and w less than or equal to 3, and that is precisely what this PB constraint means over these equality values. So it's not too hard to see that we'll be able to derive these by RUP, and that's fairly straightforward. These are just saying variables have to take at least one value in their current domain. Then we'll also derive with respect to the reason some at most one constraints. Now, I didn't show you how we can encode AllDifferent. It would be pretty clear that we could encode it, for example, using at most one constraints over all of the values in all the variables. So for example, all of the variables, at most one of them can have the value 1. That's what AllDifferent means. And at most one of them can have the value 2. And then this would just be RUP because this is just excluding values from the domains that are already excluded due to being part of the reason in the current domain state. Now, if we used a more compact encoding, for example, treated AllDifferent as being a clique of not equals constraints, we would require a little more work to derive these, but I will assert that we can still derive these. But the more interesting point is, if we have 4 at least one constraints and 3 at most one constraint, so these all have the positive coefficient 1 and these all have the negative coefficient 3, then when we add up all of these things, we're going to get complete cancellation apart from things that are not in this set of 4 variables and 3 values. So we're going to get reason implies v is equal to 1 is greater. Reason implies that negative v equals 1 is greater than or equal to 1. Now, we added up a bunch of things reified with the reason, and this nice property of pseudo-Boolean proofs is if we just run a cutting planes argument and pretend that this reason implies thing is not there, and then we look at the result that we get, then the result that we get with the reason there is going to be precisely just as if it wasn't there, but just adding the reason onto the end. I don't know if that makes a huge amount of sense, but basically we can just ignore the fact the reason is there and run our argument and trust that it's going to work out and give us reason implies whatever we derived. Okay, well now if we just add a literal axiom to this, then we've got all the way there and we've derived reason implies 0 is greater than or equal to 1. So there's a bunch of things up here. Again, the details of this argument, we have to sit down and sort of prove that this will always work on paper so that we can be confident to do it. But actually in the solver, it just amounts to writing out just a quick loop effectively to write out all of these constraints every time we derive some contradiction using the AllDifferent constraint. And then we can justify our constraint propagation in that way. So that's the real takeaway here. Okay, and the limited amount of time I've got left, and I probably should have been timing this, but hopefully I'm doing okay for time. I'll talk about one final constraint quickly. Now, I've got a lot of slides here because this was reused from my CPIR presentation on this topic, but I won't go through all of them. I'll just skip through it quickly. So a final CP constraint that really seems would be quite impressive if we could do it with pseudo-Boolean reasoning is the circuit constraint. So this works on a sequence of n variables that take n values between them. And if we're enforcing circuit, we're basically treating these as vertices in a directed graph. So to make that concrete, I'll say we have 6 variables and 6 values. And if a variable takes a value, that's saying that there is an edge between the index of that variable and the index of the value. So for example, if x2 is equal to 5, then that means there is an edge between 2 and 5 in the graph. And then the circuit constraint is saying that if we take this view of what these variable value assignments mean, then when we have a complete assignment, we must have a Hamiltonian circuit. So that is a path that starts and ends at the same vertex and visits every vertex exactly once. Okay, so this is a fun thing. This could be a useful constraint for vehicle routing, for traveling salesman type problems. Now, when CP solvers actually enforce this, they're effectively enforcing 2 things. So there's an AllDifferent constraint because this is a permutation of the variable's values. So obviously we can't have two variables equaling the same value. But then more interestingly, there is this no subcycle constraint because we could have situations like this where all the variables are indeed taking different values, but we've somehow created 2 subcycles within our permutation. So with the AllDifferent constraint and the no subcycle constraint, that is a complete enforcement of the circuit constraint. So I already said we know how to encode AllDifferent, we know how to propagate it, we know how to justify it. So really the interesting part is this no cycle constraint. So we want to enforce some kind of propagation and remove values from variables' domains. So if we had something like this, we'll write down all of the possible edges that could appear in the circuit based on these current values. And if we were enforcing domain consistency, we would remove every edge that can't possibly be part of a Hamiltonian circuit. Now, you will realize, if you're familiar with this sort of thing, that if we were able to do this, then we would be able to decide immediately whether there is a Hamiltonian circuit in any given graph. So this is, of course, NP hard to do in practice, and we don't have efficient algorithms for propagating the circuit constraint. But CP solvers kind of just say, well, we don't really care. We're going to propagate it anyway. We're not going to aim for full domain consistency. So we're not going to try and remove every possible inconsistent value. We're just going to go for some ad hoc algorithms that effectively take stock of the graph that we have and remove some edges based on properties of the graph and properties of the Hamiltonian circuit constraint. So we have these ad hoc propagators. And this is an interesting challenge for pseudo-Boolean proof logging because it means we can't just rely on figuring out a justification algorithm that will work for any domain-consistent inference, we actually have to look at these individual ad hoc algorithms and figure out how we would justify them and show that they can all indeed be justified simply by writing down PB constraints. So before we get to actually justifying them, we obviously need to know how to encode circuit. And this is something that is well understood from 0-1 ILP models of circuits. So the way we do this is we set up some more bit variables that only exist in the proof and not in the original CP model. And we say PI, so this is like a bit encoded variable, is going to encode the position of vertex I relative to 0 in the final solution. So if, for example, this was the final assignment of the variables, then we would want to constrain it such that P0 is equal to 0, P5, because this is the vertex 5, is equal to 1, P1 is equal to 2, and P2 is equal to 3, and so on. And then we have to increase the P values only until we get back to P0. So we can enforce this with PB constraints like this. So for every xi and value j in the domain of x, we say xi equals j implies that these bit values of pj is equal to, and this is just two PB constraints greater than and less than, greater than or equal to pi plus 1. So that is indeed a complete encoding of the circuit constraint. We do need to remember when we go back to 0 at the end, that's the only time this plus 1 is allowed to be violated. But it's pretty clear that this enforces circuit. Maybe you could argue this is less clear than some of the simpler encodings we put forward, but still it doesn't take long to look at it and go that, yeah, this is enforcing a distance metric effectively from the 0 variable. And so this is going to enforce the fact that we have no subcycles, which along with the AllDifferent constraint, which we have to enforce separately, is going to give us Hamiltonian circuit. So to justify a really simple propagator, which just looks at all the possible vertices in the graph and identifies things like what I've highlighted in yellow here. So these are chains of assigned variables. So the gray arrows are variables that are not yet assigned or just possible values for their domains, and the thick blue arrows are variables that are already assigned. And so we have a chain of variables here. We have x2 equals 3, x3 equals 4. Then the circuit propagator can infer, well, we better not then have x4 equal to 2, because that would complete one of these disallowed subcycles, which doesn't visit everything in the graph. So we can just remove 2 from the domain of x4. This is very simple constraint propagation, and this is something we need to be able to justify. And we can justify this very easily from this encoding that I've just showed you. So from the encoding, we have for each value in this small cycle that we're trying to disallow, a constraint like this. So x2 equals 3 implies bits of p3 is equal to bits of p2 plus 1. Then we have x3 equals 4 implies, again, this is just from the encoding, and finally this from the encoding. So we have these 3 constraints, and then we simply add them up. We use cutting planes and we add all these things together, and again, we're going to get some nice cancellation of all these all these p variables. They are also PB variables, but that's besides the point. And we get this telescoping sum. And what we're going to end up in the end is we had equal to 1 on the right-hand side of each of these constraints. So we're eventually, once we've cancelled everything out, going to get these 3 variables implies 0 is equal to 3, which is obviously trivially false. So that's just the same as saying at least one of these is false, or we can rewrite this in a different way to say this is exactly x2 equals 3 and x3 equals 4 implies that x4 is not equal to 2. So this is justifying one of those simple ad hoc circuit propagators using pseudo-Boolean cutting planes. And then we have to go through all of the other different circuit propagators, and I'm definitely not going to have time to talk about this in any detail. But another observation you can make is that if AllDifferent is enforced, then no subcycles is the same as saying that all vertices are part of one cycle, which is the same as saying that every vertex is reachable from every other vertex, and thus there is only one strongly connected component in the graph. So CP solvers can take advantage of this and say, well, if there's more than one strongly connected component, then I must have to backtrack right now because this is obviously unsatisfiable. And we can justify this in PB reasoning as well. And what we do, or what we did for this, and I won't have time to show you all the details of this argument, is we formulate a PB proof procedure, which I'm going to call reach too small, that effectively allows you to build up all the possible sets of P variables from a particular starting variable and eventually find that the set of reachable vertices is just too small and thus get a contradiction from that. So what this sort of looks like is if I'm running reach too small from 0, I would derive some PB constraints, first of all, telling me that P0 must be equal to 0. And then from that, therefore, either P1 or P5 is 1. And therefore, either P0, P1, or P5 is 2, because these are the only variables we can reach, because obviously we can't get out of this strongly connected component. And then once again, only P0, P1, or P5 could be 3. And now we've identified more possible values for these variables than we have variables in the set. And these are the only variables that can take these values. So effectively, we're in the same situation as AllDifferent. So you can probably see how we can add these up and derive some kind of reason implies contradiction from that. So that's not the actual argument. That's just kind of the structure of what the argument looks like. But the point is we have this reach too small procedure, and we can adapt it using extension variables in our proof. So using additional auxiliary variables to talk about being able to reach, or sorry, not being able to reach any vertex from any other vertex and derive contradiction from that. We can also run this whole argument conditionally on some assumptions. And what that effectively allows us to do is rewrite all of the circuit propagation rules that do a depth-first search of the graph, identify subtrees below the roots, take a partial order to see what subtrees must be visited in what order, and then remove any vertices that are inconsistent with that order. And basically, we figured out that we can formalize all of this in terms of this reach too small procedure and effectively get the CP propagator to write out the same parameterized argument every time to get a bunch of print statements that justify circuit propagation. So I'll just skip through this. There's a bunch of different cases that I talked through in my CPIOR talk that I won't talk through just here. All right, so taking stock of where we are so far in proof logging for CP, we already know how to do all of these constraints. So these are all simple fundamental constraints that probably are implemented in most CP solvers. And we know how to write down pseudo-Boolean justifications for all of them. And then more lately in my PhD research, we've been doing some of the constraints that people might have sat there in previous talks and go, okay, I understand you can do linear inequalities and maybe even equals, but you would never be able to do circuits, or you surely can't do regular language membership. And we've showed that actually, no, you can do these in pseudo-Boolean proofs. And that's just this really quite cool thing and somewhat unexpected. One that was definitely more awkward than it maybe should be for a simple proof system is multiplication, which I suppose sort of makes sense because we've got a kind of fundamentally linear constraints and we're trying to talk about multiplying these sequence of bits together, but it is doable. It was like 6 pages of a AAAI paper to talk about exactly how to do that. But certainly multiplication constraints aren't a hard barrier. And we've also identified like categories of constraints. So any constraint with an efficient smart table representation, efficient MDD representation, or any constraint with a network flow propagator or strong ILP relaxation. These are all constraints we can do. So before I finish, I was told jokingly that I wasn't allowed to graduate until every constraint was done. But what I will do in my thesis is I will go through this entire list, which is from the Global Constraint Catalog, and tick off every one that falls under one of the general categories that we've already shown we know how to proof log. And really, we've sort of found that we're most of the way there. For obviously, there are very specific constraints that are defined for very specific problems, but in terms of the standard constraints that would show up in a constraint modeling toolkit like MiniZinc, we've really covered almost all of them now, which is really exciting. There are, of course, further challenges for CP proof logging and for getting the uptake of particularly pseudo-Boolean proof logging. First of all, we have put no effort so far into particularly optimizing the output of this. So we are doing a bunch of printing in the propagation loop of our solvers, which is statistically the worst place to induce overhead. And so we do get quite painful overheads on top of solving. So you can expect the solver to be at least 5 times slower, and in some cases up to 20 times slower by turning on proof logging with our current approaches, with the big caveat that we've not really thought about how to engineer this very efficiently just yet. Also, it can be difficult to implement proof logging. You do need knowledge of the proof system and what you can and can't do. And it's maybe a bit questionable whether all CP solver authors are going to get on board with this and start learning a full pseudo-Boolean proof system to do this. So we might need some kind of proof logging libraries or frameworks in order to make this easier. There's obviously questions about verification overhead. From my point of view, that's somebody else's problem, but it's certainly something that we need to think about in order to get wider adoption of proof logging. And as I said, you could argue the Achilles heel of this approach is trusting the PB encoding or the verifier's input more broadly. Some further work that has kind of come on the back of this is turning proof logging for CP solvers into a multi-stage process, which was a paper at CP last year now. So this is the idea that if we're introducing a lot of overhead in the propagation loop and people are just interested in getting the answer out of the solver, why not just output some minimal information on the first pass of solving and then reconstruct the proof afterwards? So this is potentially a very promising approach, particularly for people that just want the answer and are maybe willing to wait a little more to get the proof later. But just to conclude the talk, if nothing else, hopefully we're on board that proof logging is worth doing, generally speaking, and that constraint programming solvers have a huge potential to be turned into certifying algorithms, and that pseudo-Boolean proof logging seems to be quite effective for a wide range of propagation algorithms. This third point is going to be the conclusion of my thesis, effectively. And in particular, high-level constraint reasoning can be reduced to simple steps in a relatively simple proof system. So we don't think we need trusted inference checkers for every constraint, although there might still be scope for having trusted inference checkers, particularly if we find, although we've not found this yet, that there are some CP constraints that are somehow fundamentally difficult for PB justifications. If that was the case, it would be interesting to think about whether we can integrate low-level proofs with these external trusted justifiers from earlier work. So there might be an efficiency trade-off with integrating, for example, a checker for the multiplication constraint rather than using our slightly nasty derivations that we had for multiplication propagation. And in general, like I mentioned, we want to think about ways to encourage uptake in the CP community and ways to get faster logging, faster proof trimming, and faster checking. So that's everything I've got to talk about in this talk. I would ask for questions, but obviously this is a pre-recorded talk. But you can find me and get in touch if you are interested in any of this. I'll be more than happy to answer any questions. So thank you very much, and goodbye.